Greetings. In this one, we'll talk about alternating groups. So, alternating groups are precisely made out of elements that already belong to a corresponding symmetric group. So, the required knowledge for this one will be symmetric groups themselves. A symmetric group consists of some permutations on k letters, and it has k factorial elements because there's k factorial permutations on k letters. And alternating groups, because they will only consist of elements that are already in symmetric group that corresponds with the same index. Symmetric group will be denoted as sub n, alternating is a, and there will be no more elements than in that corresponding Sn group, in an an group. And the thing is that there will be precisely one half the elements, because exactly one half elements will be taken from a symmetric group to form an alternating group. And I already presuppose that you know about symmetric groups, because their knowledge is fundamental to knowing alternating groups, because one first has to know the elements of the symmetric group in order to explicitly look for the alternating groups elements. So the rule that we will use is, first of all, we need symmetric groups knowledge. We also need the knowledge of cycle notation and transpositions, where cycles are a thing that I might go more closely into in another one. But in general, it's a different way of writing a permutation. And the way we determine which elements from a particular symmetry group will belong to the alternating group related to it is that we only choose so-called even permutations. That means the permutations that can be written as an even number of two cycles. And these two cycles are, by the way, called transpositions. So what is said is alternating group is only the elements from that corresponding symmetry group that can be written as an even number of transpositions, as an even number of two cycles. So we can take an example. For example, let's consider one of the not so, let's say I'm not taking two element one, I'm taking at least a symmetry group on three letters. So there's all permutations on three letters. We have numbers 1, 2, 3, and there will be three factorial different permutations. That means 6 different ones. So I will write them all. And with this example, we will see how one can go over the elements of a symmetric group and derive the elements of an alternating group from this. So this will be S3, because these are the elements of S3, because we're taking all the permutations of a three element set. So there will be 6 of them. These are all of them. And now let's determine which of them will be in the alternating group, which will be denoted as, if this was S3, this will be A3. So we only want so-called even permutations. Even permutations, as I said, are the ones that we can write in cycle notation as a product of only two cycles, as only so-called transpositions. Let's first of all take care a little bit of a reminder of what a cycle is. A cycle is a way of writing permutation. I'll use this one to show it. It's a way to write a permutation in such a way that we start with some number we choose. Let's choose, for example, the smallest one. So I start with 1 and then look where it gets mapped. Gets mapped to 2. Then I go back to the first row and I see where that gets mapped. And once I get mapped back to the same number that was in the beginning, that's where my cycle ends. So I do 1 to 2 and 2 goes to 1, but I don't write the 1 anymore. So it's 1, 2. There are some morals to consider also about, but in this case it's quite simple. Then we look for which numbers were not taken care of yet, and in this case it's just the third one. 3 maps to itself, so it's just a one cycle. I'm not writing the same number once we get back in that loop. I'm not writing it again. And one cycles, as a rule of thumb, get ignored, so they just don't get written. And we see that in this case we go to transposition straight away. In this case, in the case of this particular permutation, the cycle we got by default was a 2 cycle when doing it with this method. Now let's consider another cycle. So again, I can start with 1, I can also start with another one, but let's start with 1. 1 goes to 3, 3 goes to 2, and 2 goes to 1. So it's 1, 3, 2, and only there it goes back to 1, but I'm not writing that 1. So it's 1, 2, 3, 2, go back to the first row, 2 goes to 1, 3, 2, and 2 goes to 1. 1, 3, 3 goes to 2, and 2 goes to 1 like this. And that's where it ends the loop. So that's where we ended, and we don't write 1 anymore. And there's no numbers that were not mentioned yet, so we don't need to continue to, for example, like here, do that other cycle and only have 1 element. In this case, when we already have a cycle with 2 numbers, 2 distinct numbers, then the first one will be a single one, and we won't write it because now we have just three members of that underlying set, the permutated set. Here we have 3, and that means 3 distinct numbers, and we know that's all the ones that we can play with, and then we don't need to add any more. So we see this is a 3 cycle, but what we will really care about for alternating groups, we need to see the 2 cycles. We could go a little deeper to this and consider the fact that a cycle of odd and something called an even cycle means or something called an even permutation, as I said, means an even number of transpositions, even number of 2 cycles. The number of cycles is determined by how many numbers there are. This is a 3 cycle. And the rule is, because there's a very simple rule how to rewrite a cycle of more than 2 numbers into a product of transpositions, into a product of 2 cycles. There's a rule to follow. If a cycle has an odd number of numbers, then it can be written as an even number of transpositions. If it has an even number of numbers, if it's, for example, a 4 cycle or 6 cycle, it can be rewritten as an odd number of transpositions. So, considering the fact that we already have just 1 cycle, and we see it has an odd number of numbers, then it will be rewritable as an even number of transpositions. So it will be one of the ones we're looking for. And the concrete rule for rewriting a higher order cycle into transpositions is as follows. We can follow the rule that basically we just look at the first number, and then the second one will be the last one, and we go like this towards the left, and then 1, 3. So if there was, for example, 1, 3, 4, 5, we would do 1 4 times, and then we would go from the right like this, for example, go like this to this to this. That means this will be 5, this will be 4, this will be 3, and the fourth one is not there because that was a mistake. The fourth one is not there. We have 4. We have an even number of numbers in the cycle. That means an odd number of transpositions. So this is how it would get rewritten. But considering that theorem that odd number of numbers in a cycle or even number of numbers of a cycle results in something, can save that job of having to actually rewrite it. We don't need to know exactly the result in the cycle notation of 2 cycles yet, because perhaps when we try out if these elements really play out to be a group as well, because an alternating group will be also a group. That means that the 3 elements that we pick out of the symmetric group will play with each other, that there will be identity, and every operation between them would result in one of the 3 again. But in any case, to just return back to what we were doing is, in order to determine the elements of an alternating group, we are looking for 3 of these 6 permutations that will be rewritable as a product of an even number of 2 cycles. So this is an example, this is not an example. This is odd, this is 2, this is even. And we often, when we first look at the permutation and get a cycle, that cycle has more than 2 numbers, but that's not a problem. We are able to rewrite it very simply and very quick, or just consider that rule that I have mentioned. So let's now go over each cycle. So with this one, might have not deleted it, 1, 3, 2 like this, and that's rewritable as 1, 2, 1, 3. So that's even. And so this one is a member of that alternating group A3. Then this one we already looked at. The other one was just 3 by itself. I said 1 cycles are deleted, are not taken into account because they just lead to themselves, so they don't interfere. Well, this one is odd, so no, it's not used. So this one yes, but this one no. Then let's look at this one. So 1 goes to 3, 3 goes to 1. So that's a quick look, that's already a transposition. And the third one has to be, when there's 3 elements, has to be by itself. And therefore will get deleted. Will not get mentioned even, usually. So we have just 1 transposition, that's odd. So that's odd, and that will not be used. So so far we know that these 2 will get used. Then let's look at this one. 1 goes to 2, 2 goes to 3, 3 goes to 1. 1 goes to 2, 2 goes to 3, 3 goes to 1. So it's just one free cycle. And the way to write a higher order cycle is repeatedly use the first number, and the second one will go one by one from the very right one. So first this will be 3, this will be 2, until we reach the one just right of the first number. So also following that rule, odd number of numbers inside a cycle will result in an even number of transpositions, an even number of 2 cycles after writing it into 2 cycles. So yes, this is even, and yes, this will be a member of the A3. So we've got already two members for that A3. Now, let's evaluate this one. There's not much space, but we can perhaps do it on a smaller space. 1 goes to 1, that's by itself, won't be taken into account, and 2, 3, 3, 2 is a loop like this. So there's just 1 that's odd, and that won't be taken into account because this one is deleted straight away, like it didn't exist, and 2, 3, that's 1, that's odd. And this one now has to be, because we really need 50% of the symmetry group orders for the alternating group, and we don't only have 2 so far, and we need 3, and there's just 1 left, so this one must fulfill. So 1 by itself, 2 by itself, and 3 by itself. These are 3 1 cycles because they all lead to themselves. But if we delete all of them, then 0 remains, and we cannot write that anyhow much differently. But well, there's an option, but we can consider just the simple fact that 0 and take it as an even number. So even, and yes, this one gets included. And therefore, the 3 ones that we chose was this one, and this one. And these 3 will be the A3 alternating group. So that's 1, 2, 3, and 1, 2, 3. The second one, 1, 2, 3 going to 3, 1, 2. And the third one is 1, 2, 3, 2, 3, 1. Now we can try it out. We can try if taking any 2 of them will lead to, again, getting into the sum of the 3 that belong to the alternating group, that there is this closeness of operation. And by the way, the operation again will be function composition, because these permutations, they are bijective functions defined by a matrix, but that's why the knowledge of symmetry group and traditional permutations is required for it. So let's just test it. Let's just test if this works out. Of course, with the identity, if we put either of these 2, they will just stay the same. So we know that already. We do have an identity. And then we can try to put these together only with each other, because we just have 3 elements, two of them are not the identity. So the only things we can really take care of is we can put them together in operation. So 1, 2, 3, 3, 1, 2, and then the second one, 1, 2, 3, 2, 3, 1. And so let's try it out. We compose the functions, and this was shown in the permutation video, a permutation group video. Well, that we first look at this bijective function, and then we carry that information to the left one. So 1 goes to 2, and 2 goes to 1. So it's like this. or we can actually write it in permutation notation. Permutation matrix notation. So 1 goes to 2, and 2 goes to 1, so that's 1 to 1. 2 goes to 3, 3 goes to 2, so it's already assuming it will be the identity. Now let's try to switch the 2. So we will have 1, 2, 3, 2, 3, 1, an operation with 1, 2, 3, 3, 1, 2. And see how that ends up. So 1 goes to 3, 3 goes to 1, 2 goes to 1, 1 goes to 2, and the third one will also end up as fulfilling the identity pattern here. And so we see in both cases it goes to the identity. So they're actually inverses of each other, and it even works commutatively, which is the expected state. So yes, we determined this alternating group, and this was just an example. Of course, software can be used for higher order alternating groups because then we are considering a lot of permutations. Perhaps for the cycle notation, another information is, yes, there's more ways to write a particular permutation in cycle notation. There's more cycle notation, various ways to write it. So one can, the cycle expression can be altered many times, many ways. But the thing that's consistent is that if it is once written as an even, if that permutation is writable as an even permutation, as an even number of transpositions, then even if we change the number of the transpositions, or if we modify how the transpositions inside the numbers, turn them around or something, always it will be writable as an even number of, always it will end up as an even number of transpositions. And if it was odd, it will always be odd number of transpositions again. Yes, the exact look of that cycle notation, even in the two cycles, can change in many various ways, but no matter what chosen way it is written in, if it's already an even permutation, it will stay, and no matter what way we choose to write it as a product of two cycles, if it was even before, even if we change the way we write it, still it can be, instead of 6 two cycles, it can be 8 or 10. But it cannot become an odd number, even if it's rewritten in many different ways. So there's some information to the cycles, but otherwise, the alternating group has interesting applications in the theory of finite simple groups, and therefore it's quite a considered one. And again, to just sum up the important information, it has half the order of a corresponding symmetric group, so when we had S3, now this will have half that order. Of course, it's a group, so it's closed, it has inverses. And it turns out that if we take that specific head of the symmetric group's elements, they have all these properties that the group has by itself.